Okay, now we will see next example for the structural determination by stereochemistry, differential stereochemistry with the help of NMR spectroscopy. So we will see now the reaction double aldol condensation. So here is the ketone we have taken, and we will react with the aldehyde in presence of strong alkali. It will give this type of product. Okay. So now we will take another example. We will take this type of ketone and we will take parachlorobenzaldehyde in presence of hydroxide and water. What will be the A? What will be the product? Okay. So as in this compound we will get this alpha beta unsaturated carbonyl compound like that. We are expecting the same thing from this reaction. So let's see what is the A molecular formula C19H8H18 Cl2 Cl2 go to delta is 7.7 hydrogens. Then at 4.49 2 hydrogen doublet J decoupling cost 10.4 2.98 2 hydrogen doublet of quartet doublet and quartet coupling cost 10.4 and 6.6 and 1.08 6 hydrogens doublet J 6.6. Okay, so we'll see now what will be the options of the product of this A. Okay, so we have NMR values in our hand. With the help of NMR values we will try to deduce the structure. Okay, so what are the possibility? So possibilities are like uh, 2 moles of parachlorobenzaldehyde, they will react with this molecule, join up in this region. The reaction between pentane 2-one and 4-chlorobenzaldehyde, a different product is formed, not like previous one. The mass spectrum shows that two aldehydes have reacted with one ketone as usual, but that only one molecule of water has been lost. Some of what we know about the compound is shown in the scheme. The C13NMR spectrum shows that there is one ketone carbonyl group as expected, but no alkene carbons. There is no formation of alkyl carbons. NMR spectrum, C13 NMR spectrum is showing. There is only one set of C13 carbon signal for the 4-chlorobenzene, 4-chlorophenyl ring, and only two other carbons. Okay, with the help of C13 NMR, we come to know that there is one ketone carbonyl group is there, and but there is no alkene carbons, and only one set of signals, only one set of C13 signal for 4-chlorophenyl ring and only two other carbons. This must mean that molecule is symmetrical. So we will see now how to synthesize a symmetrical molecule on the basis of the proton NMR data. Okay, so here 2 moles of parachlorobenzaldehyde and 1 mole of this ketone. So structure might be like this. Okay, with there one carbonyl group is present. Okay, two methyl group is already present there, but there is no formation of carbon-carbon double bond. But cyclization is there. The proton NMR spectrum gives the answer. Both methyl groups are still there, and they are identical. Yes, two methyl groups are present. So we have two identical MECH fragments. So MECH. Okay. So we have this carbon, hydrogen, black colored hydrogen attached to the carbon, and same the methyl group. These CH protons are double quartet, so that they have another neighbor. Okay. So this proton shows double quartet. Okay. The only remaining aliphatic protons, actually again two identical protons in green at delta 4.49 ppm. Okay, so this green hydrogens appears at delta 4.49 ppm, having doublet. Okay, so this hydrogen will get coupled with this black colored hydrogen, and this black colored hydrogen is coupled with methyl group hydrogens as well as this green colored hydrogen. Okay, so the proton must be next to both oxygen and the aromatic ring to have such a large shift. But there is only one spare oxygen atom, so the protons at 4.49 must be next to the same oxygen atom. The structure is shown on the on this page. Okay. So this is the now if this that kind of structure with metallized product we will get, then now how to deduce or how to identify at which position who is present. That means two methyl and two aromatic groups are there. Now we have to go for the stereochemistry of this one. So in one structure, both methyl group and aromatic group, they should be opposite to each other. Either they should be opposite to each other, or they should be on the same side of the ring. Okay, on the same side of the this cyclohexane chair conformation. So here I have drawn the cyclohexane chair conformation, and now in first one where methyl and aromatic they are trans to each other, so methyl to methyl. So methyl present above the plane, this methyl is also present above the plane, and at the same time this aromatic and this aromatic group present below the plane. Okay, so in this case these two are aromatic sorry trans to each other. And another possibility of structure formation is methyl group, they are present above the plane. Also aromatic, two aromatic rings also present above the plane. Okay, so this will be the possibility of the formation of the product. Now with the help of coupling constant, we have to finalize that which structure is forming. Okay, so the coupling constant between hydrogen atom is 10.4. Okay, so as we know, if coupling constant is highest, that means that means more than 9 hertz, so definitely there must be the hydrogen must be the axial. Okay, so here hydrogen in black colored hydrogen, so they are present axially here. Now which protons, that means green colored hydrogen atoms, they are vicinal to these black colored hydrogen atoms. Okay, so these vicinal hydrogen atoms, they are also axially placed. Okay, so pay attention at the hydrogen atom which are in black color and hydrogen atom which are present in green color. So these two hydrogen, they vicinal hydrogen, they are vicinal to each other as well as they are opposite to each other. That means there must be the angle in between these hydrogen yeah, black color hydrogen and green color hydrogen, the angle must be the 180 degree centigrade, and due to this angle 180 degree centigrade angle, their coupling constant is also highest, that is it is 10.4. Okay, so same thing in this case, this black colored hydrogen and this green colored hydrogen, this the angle in between these two hydrogens is 180 degree centigrade. So that's why the coupling constant is 10.4 hertz. So this the coupling constant value of these two hydrogen indicates that these two both hydrogens, all four hydrogens, they are anti to each other. So the final structure what we are getting, as these four hydrogens they are axially placed, that means the remaining bulky substance they must be the equatorially placed. Okay, so here if we will write or the structure as according to that one, so methyl group which are if hydrogens are axially, then methyl groups must be the equatorially placed. If these two hydrogens they are axially placed, then aromatic substance there must be the equatorially placed. Okay, so in that way methyl groups, both methyl groups, they are present above the plane, and both aromatic rings or both aromatic substances present below the plane of the paper. So in this way now we will if we will write the structure in this way, so we will get methyl and aromatic rings, they are trans to each other. Okay, so this is the way, this is the beauty of this technique to identify the different structure after different reactions.